The fundamental theorem of calculus helps us evaluate definite integrals using antiderivatives. We can also go in reverse, using integrals to define and construct antiderivatives. Number one says, suppose we've got a function capital G of t whose derivative always equals some function little g of t. In fact, little g of t is the graph that you see. We also suppose capital G of 0 equals -3. Why -3? It's really an arbitrary choice. Part A says to use the figure shown below, this graph of little g of t, to find the values of capital G of t, not its derivative, at different values of t, 5, 10, 15, 20, and 25. And then in part B, we want to give a rough sketch of the graph of capital G of t. The derivative of capital G equals little g. Therefore, capital G is assumed to be an antiderivative of little g, or antiderivative if you prefer. And we're going to use the fundamental theorem of calculus to help us do this problem. The FTC says that the integral from a to b of some function, like the function little g of t whose graph is shown, can be evaluated by, if you know an antiderivative, like capital G, doing capital G of b minus capital G of a. However, in the usual way that we use this, it's not really helpful here because we don't know a formula for capital G. So what is the point of using the fundamental theorem of calculus here? It's to evaluate these values, these differences, and this assumption using the integral, using the signed area interpretation of integration. And fortunately, in this case, the area under the curve is made up of a bunch of squares, or actually they're rectangles because the base and height are different here, and triangles. And we can think about the signed area interpretation of integration to help us evaluate these integrals. All right, so what do we want to do? We want to evaluate capital G of b minus capital G of a for different values of a and b by doing the integral. That's the same as the change in g in each case. And what we're going to do is we're just going to build a table of values of capital G to help us graph it ultimately and think about the fact that its derivative is what you see here, little g. So let's pick some different values of t. And then we'll also evaluate values of capital G of t. T equals 0, 5, 10, 15, and 20, and 25 is what we're after in the problem. We're assuming capital G of 0 is -3, so that part is easy. Again, that's an arbitrary assumption. We could have assumed something different. What about capital G of 5? Use this equation. We can, in fact, think about it by adding capital G of a to both sides if we like. We can write capital G of b equals capital G of a plus the integral from a to b of little g of t. So what does that mean? That means that at t equals 5, we take the value of capital G at 0. That's going to act like the a is t equals 0. And add the integral of little g of t from 0 up to 5. The integral of little g of t from 0 up to 5, which by the signed area interpretation of integration, since over here the graph of little g is above the axis, it's going to be the area of this thing that looks like a square, but if it were the scales and the axes were the same, you'd see it's really a rectangle. Base is 5, height is 2. That integral equals 5 times 2 equals 10. That is the change in the value of capital G over the interval from 0 to 5. Therefore, capital G increases by 10 from -3 up to +7. Okay, that'll be the value of capital G at 5. What about its value at t equals 10? Use this formula again with a equal to 5 and b equal to 10. Take the previous value, 7, and add the integral of little g from 5 to 10. The integral is going to represent the total change in capital G. Its starting value at t equals 5 is 7. How much does it change over the interval from 5 to 10? That gets added to 7 to find the value of capital G at 10. What is that integral? It's the area of this trapezoid. The area of a trapezoid is the base, which is 5, times the average of the heights. The height over here is 2. The height over here is 4. The average of 2 and 4 is 3. 5 times 3 is 15. That's going to be what the integral is. You also could see that this rectangle is the same area as that one, 10. And this is a triangle with half the area, 5. 10 plus 5 is 15. another reason the integral value is 15. That's the total change in capital G. So capital G increases from 7 up to 22 as t increases from 5 to 10. How about at t equals 15? Once again, take the preceding value, 22, and add the integral, in this case from 10 to 15, of little g of t dt. That'll be the area of this trapezoid, which you can see by symmetry is the same as the area of that trapezoid, 15, bringing us up to a value of 37. When t equals 20, we take the previous value, 37. Let me do this to help us distinguish what's going on here, and add the value of the integral from 15 to 20. What is that value? It's the area of this triangle. Base is 5, height is 2. 1/2 times base times height will be 5. So we add on 5 here. That's the total change in capital G. So we get up to 42. And finally, capital G of 25, we'll take that preceding value, 42, add on the value of the integral from 20 to 25. However, this time the value of the integral is negative because the graph is below the t-axis. The area of this triangle is 5 again, but it needs to get subtracted from the value of the integral. The integral is equal to -5. So I could write this as 42 plus -5, or 42 minus 5 if I prefer, to get a value of 37. Okay, so these are the values of capital G at these different values of t, -3, 7, 22, 37, 42, and 37 again. We can use those plus thinking about slopes to help us graph capital G. At t equals 5, t equals 10, t equals 15, t equals 20, and 25 again. Make our scales so maybe this is 40, this is 20, 10 would be right here, 30 would be right here, -10 would be down here. Getting those scales approximately right there. When t equals 0, capital G of 0 is -3. So that point 0, -3 is on the graph of capital G. When t equals 5, capital G of 5 is 7. So we go up to 7. That'd be right about here, say. When t is 10, the output is 22. So right about like this. It's kind of looking like a straight line. It's not. It's a little deceiving. My scales may not be perfect. Capital G of 15 is 37, so we get up to about here or so. Capital G of 20 is 42, so we get slightly above 40 there, and then we go back down to 37 when t equals 25. So now I could connect the dots, but you should be careful here. The slope of capital G between 0 and 5 is constant because the output of its derivative is constant at 2. So this is a straight line right here. However, between t equals 5 and t equals 10, the slope of capital G, the derivative of capital G, is not constant anymore. It's a linearly increasing function. So that means the slope of capital G has to be linearly increasing. It's got to be parabola-like. A little bit subtle here. Technically, the slope right there should be the same as the slope of this. The slope of this, by the way, is 2. So the slope right there, the tangent line does exist and equals 2. I kind of exaggerated there to try to emphasize that it is concave up because little g, its derivative, is increasing. Then between t equals 10 and t equals 20, in fact, little g decreases, capital G prime decreases, the slope of capital G becomes smaller. It's going to be concave down in here. This will be an inflection point. At t equals 20, the slope of capital G, which is the value of little g, is 0. Horizontal tangent right there. It's a local max for capital G. And it continues to be concave down because little g is decreasing in value. But now capital G has a negative slope. So there's a decent approximation of the graph of capital G, and I've finished the problem. Number 2 is purely symbolic, no graph given. Let capital F of x be an antiderivative of little f of x. So that means that capital F prime of x always equals little f of x, no matter what x is. Part A says, if we assume that the integral of little f from 3 to 7 is 8, and capital F of 7 is 12, find capital F of 3. And we also have a part B. Once again, we can use the fundamental theorem of calculus. We're trying to find the value of the function capital F at 3. We know its value at 7. We also know the value of its derivative, of the integral of its derivative from 3 to 7. The fundamental theorem of calculus is relevant here. 8 is the value of the integral from 3 to 7. But by the fundamental theorem of calculus, since we are assuming capital F is an antiderivative of little f, this is capital F of 7 minus capital F of 3. We are given that capital F of 7 is 12. So now all that's left to do is solve for capital F of 3. Add capital F of 3 to both sides of the equality between 8 and this, and then subtract 8 from both sides. Therefore, capital F of 3 is 12 minus 8 is 4, and that's the answer. For extra confirmation, you see that capital F increases in value from 4 to 12. It increases by 8 units, and that is the same as the value of the integral. It's given to be 8. So a little bit tricky, but definitely doable. Part B, assume that the integral of little f of x from negative 4 to 27 is 0. What is the relationship between capital F of 27 and capital F of negative 4? I hope you can figure it out without even writing anything down. They have to be equal. Why? They are equal. F of 27 equals F of negative 4. Why? Because by the fundamental theorem of calculus, 0, which is the value of the integral from negative 4 to 27 of little f of x dx, is capital F of 27 minus capital F of negative 4. Just add capital F of negative 4 to both sides of this equation, and you get this. They are equal. Okay? This function, little f, has an integral equal to 0. That doesn't mean it's always 0. It could go both above and below the axis. If it goes above the axis, it's got to go below, because the signed area interpretation says that the area under the graph when it's above the axis minus the area above the graph when it's below the axis gives you the value of the integral, which in this case is 0. Capital F, if little f is above the axis over here and below the axis over here, capital F will be increasing over here and decreasing over here. Ultimately, the change in capital F over this interval is 0. Number 3 is a little tricky graphical problem for the function little f, whose graph that you see below, for which one antiderivative, capital F, has a graph that goes through the origin. Now, there are actually infinitely many antiderivatives. They all differ by a constant, which are vertical translations of each other. We want a particular antiderivative whose graph is assumed to go through the origin. And we want to find the value of c that you see right here, such that capital F of 5, where 5 is over here, equals 0. This area minus that area must equal 0. We want to find c so that the integral of this function little f of t from 0 to 5 equals 0. Why? Because by the fundamental theorem of calculus, the value of this integral is capital F of 5 minus capital F of 0. Capital F of 0 is assumed to be 0. Therefore, this is capital F of 5. And that's what finishes the problem. We want capital F of 5 to be 0. Therefore, we want this integral to be 0. We want this area and this area to cancel out in terms of their contributions to the integral. So we better figure out these areas in terms of c. This area is the area of a semicircle. 1/2 times pi times the radius squared. What is the radius? Careful, it's not c, it's c over 2. That is assumed to be a semicircle, by the way, if you didn't realize that. C over 2 is the radius. That's got to get squared. This simplifies to pi times c squared over 2 squared is 4 times another 2 is 8. That's what that area is as a positive quantity. What about this area as a positive quantity? Well, it's a rectangle. Base times height. The base is 5 minus c. We're assuming c is less than 5, so that's a positive number. The height is not negative pi over 6, but positive pi over 6. Yes, that's negative pi over 6 on this axis, but as far as a height in the ordinary sense, the height is pi over 6, positive pi over 6. We want to choose c so that these are equal, so that when they contribute to the integral as this minus that, you get 0. Say that again. We want to choose c so that these are equal, so that when you do the integral and get this minus that, you do get 0. So we need to set them equal to each other and solve for c. Set 5 minus c times pi over 6 equal to pi c squared over 8, and solve for c. The pi's cancel. C will not be simply related to pi at least. And we get c squared over 8 on this side. I can multiply both sides by 8. I can say 5 minus c times 8 over 6, which is 4/3, equals c squared. We've got a quadratic equation in c. Not so simple. I probably need to use the quadratic formula in the end. Let's distribute this through the parentheses. 5 times 4/3 is 20/3. Minus 4/3 c equals c squared. Let's get everything on one side with 0 on the other side. 0 equals c squared plus 4/3 c minus 20/3. If you prefer, you can multiply everything by 3 and say 3c squared plus 4c minus 20 equals 0. And then we probably want to use the quadratic formula if we can't factor it very easily. You can factor this, but let's use the quadratic formula anyway. C equals the negative of this coefficient. This coefficient is positive 4, so I get negative 4 plus or minus that thing squared, 4 squared, minus 4 times 3 times negative 20, all over 2 times the coefficient of c squared, which is 3. 2 times 3 is 6. Negative 4 over 6 is negative 2/3. Plus or minus 1/6 times the square root. What do we have in here? 4 squared, 16. 4 times 3 times 20 is going to be 240. And we're going to be adding that because two negative signs make a positive sign. This is going to be a square root of 256, which is 16. So we get negative 2/3 plus or minus 16/6, which is 8/3. You can see obviously in this picture that c is a positive number, so we want to pick the positive root. C is going to be negative 2/3 plus 8/3, which is 6/3, or 2. That seemed like a lot of work to get such a simple answer. C equals 2 is the answer. You may want to double check that by going back up to these areas and plugging in c equals 2. What would we get with this one when c is 2? We get pi times 4 over 8, which is pi over 2. That would be the area of this semicircle. And what about the area of this rectangle when we plug in c equals 2? 5 minus 2 is 3. 3 times pi over 6, which is, once again, pi over 2. We have a match. That confirms the answer, which is c equals 2. In problem number 4, we will need to use technology. If capital F of 0 is negative 1, the negative 1 is arbitrary, and capital F of x is an antiderivative of this function right here, use a calculator to estimate capital F of 2. And we really will need a calculator here. This function has no elementary antiderivative. It doesn't have a simple formula for capital F of x. Technically, theoretically speaking, capital F of x does exist, though that requires another part of the fundamental theorem of calculus to prove. Let's think about this in the abstract. Once again, the FTC would imply that the integral of little f from a to b would be capital F of b minus capital F of a. Thought of another way, capital F of b minus capital F of a is the integral from a to b of its derivative, which is little f of x. What should we use for a and b? Probably we should use a equals 0 because we know what capital F of 0 is. So this becomes a negative 1 right there. And b, well, that would be 2. And in general, b could be anything. I mean, the 2 is arbitrary as well. You should realize that in the context of this problem, we could represent capital F of b at an arbitrary value of b abstractly as capital F of a plus the integral from a to b of little f of x dx. And if we take a to be 0, that's the same as capital F of 0 plus the integral from 0 to b of little f of x dx. And capital F of 0 is -1. This becomes -1 plus the integral from 0 to b of little f of x dx. I'm emphasizing this abstract viewpoint briefly here in this problem because it is important for the other part of the fundamental theorem of calculus. We don't have a simple formula for this, but the relation that capital F of b for an arbitrary value of b equals -1 plus this integral is still true. This essentially does define capital F of b as an antiderivative. Now we might need to approximate that integral either with a calculator, numerical integration in a calculator, or some numerical integration scheme that you try to do by hand, maybe with calculator help. But as a principle that these two things are equal and that this formula essentially constructs an antiderivative of little f, that is the other part of the fundamental theorem of calculus. You could say that capital F prime of b equals the function little f of b, replace x with b, for all b. That is true, and it's something I wanted to mention. Now let's go ahead and take b to be 2. Capital F of 2 is -1 plus the integral from 0 to 2 of little f of x dx. Now is where we use the calculator to approximate that integral. The integral represents the change in capital F as x increases from 0 to 2. Whatever that integral is, it gets added to the starting value of capital F at 0, which is -1, to get the final answer for capital F of 2. Go to my calculator. I'm going to graph. The function is 4 times e to the negative x squared. Going to graph this on the window between 0 and 2. I'll make y go from 0 to 4. Let's see what the graph looks like. It's kind of like an exponential decay, except with a bit of a curve at first where it's concave down. It's actually related to something called the normal distribution. It's not exactly a normal distribution, but it's related to it. What is this area? Go to my calculate menu, go down to the integral. My lower limit of integration is 0. My upper limit of integration is 2. This area is approximately 3.5283256. Let's write that number down. This is approximately -1 plus that number, 3.5283256. And assuming the calculator is accurate to that many decimal places. Again, that's the change in capital F as its input increases from 0 to 2. But again, its starting value is -1, so the final answer is this thing -1. That'd be 2.5283256. And make sure I wrote down all my numbers correctly. This does look right. That's capital F of 2 approximately. Our last couple problems are going to continue to involve graphs. Number 5 says use the figure below to sketch the graph of an antiderivative capital G of t when this graph is little g of t, satisfying capital G of 0 equals -8. Label each point as each critical point of capital G of t with its actual coordinates. And I think if we can, we'll also maybe try to identify approximate inflection points. Not exact, but approximate. Once again, the fundamental theorem of calculus is relevant. At an arbitrary value of t, I could call it b, but here I'm calling it t, capital G of t minus capital G of 0 would be the integral of little g from 0 to t. I could also add capital G of 0 to both sides. So I can write at an arbitrary value of t, capital G of t equals capital G of 0 plus the integral of little g from 0 to that number t. Now I purposely switched from a b to t here to kind of get you used to this. It's a little strange, but they represent arbitrary numbers anyway. It doesn't matter what letter they are. However, if I do put a t up here, I should probably put something other than a t for the input for little g here. How about the Greek version of t? Tau. Integral of little g of tau d tau as tau goes from 0 to t. Tau is kind of a pretty looking t. It's the Greek version of t. Don't let the symbols bother you. This is certainly fine. It can be done. We're assuming capital G of 0 is -8. So we can write this as -8 plus the integral from 0 to t of little g of tau d tau. What's my goal? My goal is to use this graph to sketch the graph of capital G and also find values of capital G at the critical points of it. So I need this integral, and I need to think carefully about slopes of capital G, because the little g is the derivative of capital G, so the outputs of little g tell you the slopes of capital G. Where should we put, if I try to draw capital G on the same axes here, where should we put -8 and +8? Well, we can approximate it. This area that you see here is labeled to be 16. It's not a triangle, but it's close to being a triangle. With base 2 and height unknown, area of a triangle is 1/2 base times height. 1/2 times 2 is 1 times the height. It's supposed to be 16. So the height is approximately 16. Now it's, again, not exactly a triangle, so 16 is going to be somewhere right around there, meaning 8 is going to be somewhere right around here. Let's just pretend it's there. And -8 would be down here. Capital G of 0 is -8. This point is on the graph of capital G. And in fact, the slope at t equals 0 is 0 there because the value of little g of 0 is 0. It's going to be a horizontal tangent there. And then the graph is going to be positive in slope because little g has positive values. It's going to be concave up. As t increases from 0 to 2, capital G of 2 is -8 plus the integral from 0 to 2 of little g of t dt. And I can, by the way, go back to t's here if I like. Maybe I should stick with tau's, though. Little g of tau d tau. Don't let it bother you that tau there and t there don't match. It's not a big deal. The integral is that area, 16, because that's where the graph is above the axis. So the change in capital G over this interval is 16. Therefore, the value of capital G goes from -8 up to +8 as t goes from 0 to 2. So it's got, value's got to be 8 over here, and it reaches a maximum slope at this value of t, which is right about there. That's going to be an inflection point for capital G. It's hard to say if it's going to be above or below the axis there. Actually, it's going to probably be below because this area to the left of this line is less than this area to the right. So yeah, this is getting pretty accurate, I think. Something like this is the graph of capital G from 0 to 2. How about from 2 to 4? Capital G of 4 is -8 plus the integral of little g from 0 to 4. I could have changed the a from 0 up to 2 if I wanted to. This integral of little g from 0 to 4 is 16 minus 8. 16 minus 8. The integral from 2 to 4 is -8. That's an 8 there. -8 plus 8 is 0. Capital G of 4 is 0, and that's got to be where the slope of capital G is 0 as well, because the value of little g is 0 there. Notice the slope here is 0 as well. We got to go down to 4, maximum negative slope. Absolute, I should say smallest negative slope is right or close to t equals 3. So something about like this. And again, capital G of 4 is 0. Inflection point for this part is going to be right around here where the graph of little g is most negative. And then between t equals 4 and t equals 5, the graph of capital G will increase again. What is the value of capital G of 5? It's -8 plus the integral from 0 to 5 of little g. -8 plus, in parentheses, that integral is going to be 16 minus 8 plus 2. That's a 10. -8 plus 10 is 2. So we go up to 2. If 2 is right about here, say, we don't go up very far here. Something about like that would be the graph of capital G. What are the critical points where the derivative of capital G is 0? This point is a critical point, 0, -8. This point here is a critical point, 2, +8. This one's a critical point, 4, 0. And this one's actually a critical point as well. The graph's, there's actually an inflection point right about there. The graph's concave down after that point. Right about there at 5, 2 would be your last critical point for capital G. Our last problem is similar, except we don't have areas well defined here. We want to sketch two functions, capital F, that are both antiderivatives of the given function, little f. For one, let capital F of 0 equal 0. For the other, capital F of 0 is assumed to be 1. Mark x1, x2, x3 on the x-axis of your graph. Identify local maximum, minima, and inflection points of capital F. The way this is phrased, we should draw another graph. But I've already got a scale here with x1, x2, and x3 on it. So why don't we go ahead and use that. For the first case, capital F of 0 is 0, so this point is on the graph. The slope when x is 0 is positive because little f is positive in value there. Little f of 0 is positive, so capital F prime of 0 is positive. It's not a critical point there. At x1, that's where little f has a value of 0, so the slope of capital F has to become 0. That will be a local max point for capital F. We decrease now because little f is negative. It's most negative in value at x2. That'll be an inflection point of the graph of capital F. Right about there, say. And then the slope is still negative because the value of little f is still negative, but it's increasing. Little f is getting closer to 0, so the slope of capital F gets closer to 0. And at x3, we're going to have a critical point that's going to be a local minimum for capital F. And then it's going to increase this positive slope thereafter because little f has a positive slope. And it does continue increasing here, so this continues to be concave up. So there is an approximation of capital F when capital F of 0 is 0. When capital F of 0 is 1, we just shift this graph up by 1 unit. Now we don't know where 1 is on this axis. Could be up here, could be down here. Let's just pretend it's here. This graph is the exact same graph shifted up by 1 unit. Something about like this. In both cases, x1 is a critical point of capital F giving you local maximum. x3 is a critical point of capital F giving you local minimum. And x2 is an inflection point of capital F. How do you tell that from the graph of little f? That's where little f changes from decreasing to increasing. Therefore, capital F changes from concave down to concave up as x increases through x2. Thanks for watching.